Yo, what's up everyone? This is LeetCode 322 coin change. So we are given an integer array coins representing coins of different denominations and an integer amount representing a total amount of money. So we have to return the fewest number of coins that you need to make up that amount. If that amount of money cannot be made up by any combination of coins, return -1. Okay. You may assume that you have an infinite number of each kind of coin. Now, this last line here is actually really important in an interview, right? Because you wouldn't want to make this assumption if it's not explicitly told to you. Um, so yeah, in an interview, right, you make sure you actually verify that this is the case. But anyways, so over example 1, right, we have the amount 11, and we have all these coins here. Right, my bad. I was zooming in because if I zoom out too much, you might not be able to see. I just zoom out just so I can have a clear view of both windows. But anyways, my bad. I want to zoom in a little. Okay, so we have these different types of coins, right? A 1, 2, and a 5, and we have to make up the amount 11. Now you could use like 11 1 coins to make up the amount 11, but you're not returning the fewest number of coins needed to make up that amount, because we could use a 5 coin, and a 1 coin to make up the amount 11, and that's only 3 coins, which is less than 11. So, yeah. So I hope you understand what this problem is asking, right? We just have to use some combination of coins to make up amount. There can be different combinations, and you want to basically pick the combination that makes up amount. You want to use the combination that uses the fewest number of coins possible. And there are cases where you can't make up amount using any combination, and that's like a case where you return -1, okay? Now, if we go to topics, you'll see this problem is a DP problem, right? Dynamic programming. But it's also a breadth first search problem. And we're not going to use breadth first search to solve this problem because it's a little bit less optimal, but I'll draw it out, right? So you can imagine that if we have a decision tree like this, right? We have 11, which is our amount, for example, 1, right? And we're using different combinations of coins to find out, right, if we can make up this amount, right? 11 minus 1 gives us 10, 11 minus 2 gives us 9, right? 11 minus 5 gives us 6, right? And we basically keep breaking our decision tree down, right? And at some point, we're going to reach maybe like a place where we have a 0, right? That means that is a valid path for the combination of coins, right? And this could exist in multiple different places, right? And really, the reason you could use breadth first search on this problem is because you basically would just find the shortest path, because that would give you the fewest number of coins needed to make up amount. So the shortest path to whatever, to some 0, that leads to a 0, okay? So I hope that makes sense why you could use breadth first search on this problem. But we're not going to use that because it's, I think, a little bit less optimal. Also, I've never seen someone solve this problem using that method. Probably because it's not optimal. I don't know, but yeah. But you can do it that way. I'm pretty sure. I personally have never seen it done that way. But that way. So I'll show you how we're going to solve this problem. Okay. So we're going to go through example 1, right? And first, let's consider also, could we use a greedy approach, right? Right, like use the largest number of coins to make up amount, right? And you can't. Okay, you can't use a greedy approach, right? And I'll give you this example here, right? If we have these coins, right, 1, 4, and 5, and we have an amount 8, well, if you use the biggest coins first, you might think, okay, we have 5, a 1, a 1, a 1. Oh, okay, we'll just return 4. We use 4 coins, right? But that wouldn't be valid, or it would be valid, but it wouldn't be the correct answer, because we could also use 2 4 coins to give us 8, right? And so as you can see, the greedy approach obviously wouldn't be the most optimal. It wouldn't, not just optimal, but it wouldn't be the correct approach. Because we would have to return 2, not 4. So anyways, I'll show you how we're going to set this up. And, you know, for this problem, you can do it recursively or iteratively. Since it's dynamic programming, I'm not going to bother with the recursive solution. I think it's a little bit less easy to read. It's less optimal, right? It's less, I don't know. I think it's less easy to understand also. So we're just going to do it iteratively, which is honestly the easiest way to understand and implement this problem anyways. So we're going to create a DP array, right? And the length of the DP array should basically be created using the amount, right? Plus 1, right? So 11 plus 1. So our DP array, for example, would be 12, right? We have a 0th index, so this is size 12, okay? And we want to populate every place in the array with infinity, right? Those are just like our placeholder values, right? DP of 0, the 0th index, should be set to 0 because there are 0 coins needed to make this amount 0. And really, you can think of the way we're going to do this is just like this. We're going to go through this array, and we're going to calculate the amount needed to make each position. And obviously, this last index here is basically the grand prize, right? It's what we want to get to, because we want to find the fewest number of coins needed to make up the amount, which is 11. Okay, and the reason we do it like this, by the way, is because we're using at some position we're using previous stored results to basically retrieve the fewest number of coins possible. And you can imagine why this is done this way, right? But in case you can't, if we have like some numbers, right, for this decision tree, now you can imagine this decision tree is very simple here, but it can grow very large, right? If you could have a lot of coins, and if you have a big number. And so, right, if you have some path, right, and you have another path, and they use the same combinations, right? Maybe they branch out and do something different, but they use kind of like the same number of coins, like, you know, like a 5 and a 1. Well, sorry. Like a 1 and a 5. And then here you do like a 5 and a 1, right? They use the same coins, really. So you wouldn't want to recompute stuff. Or maybe that's not a correct example, actually. Maybe, you know, here you would have maybe a 1 and like a subtract a 5. Then here you would have like a 1 and a 5, right? You get the point. Like you basically want to cut down on reducing work when you have 2 points in the decision tree that basically have the same result, right? Which is obvious, right? Because that's kind of the point of you know, solutions to dynamic programming problems, is you want to reduce basically redundancy and overhead, to not have like a really big time complexity, right? That's all I'm getting at. Okay, but anyways, back to the problem. So that's how we're gonna use this, right? We're gonna use previous stored results to basically make an efficient solution, right? That is very fast. Okay, and the way we're going to solve this, okay, is I'm going to explain it like this, okay? So these indexes here are basically just the amount we need to make at the given index, right? The given index is the amount we need to make using some combination of coins. And here, these answers are in the actual array. They're the minimum amount needed to make up our amount, or the minimum amount of coins, okay? So we're going to start here, obviously, because this is our placeholder, right? So we have a current amount of 1, right? And we're going to iterate through coins, by the way, for a given index, right? So we're going to start here, right? We're going to do 1 minus 1. This is our coin, remember, that we're subtracting. Okay. And the way we're going to calculate what we need to put here is we're going to basically use this formula here, okay? So we're going to do the minimum between basically the DP of the current amount. Well, at the DP at the current amount, remember, this is the current amount. Initially, it's 1, right? So DP current amount, which is DP of 1, is infinity, right? So we have to take the minimum between infinity and what? The DP current amount minus coin. So DP, this is current amount, this is coin, so 1 minus 1 gives us 0. So we do 1 plus 0, right? That gives us 1. Well, what's smaller, 1 or infinity, right? That's pretty obvious, 1 is smaller, right? So the DP at the current amount, so the DP of 1 gets set to 1, okay? So backtrack here. So the DP of 1, it's set to 1. This video might be a little bit long, by the way, but I'm going to go through the whole example because some videos don't do that, and I think they actually are a little bit confusing if they just give you the code. I'm just going to kind of go through it just to explain to make sure you understand what's going on with our solution. Okay, so then we're gonna do the same. And by the way, we're gonna do that for the other coins too, right? So at this one, we're still at this one here. So we're gonna do 1 minus 2, right? But obviously that gives us a negative number, so we're gonna skip it, right? Okay, let's go to this 5. 1 minus 5, that gives us a negative number also, so we're gonna skip it. But you know, even if we add something here to replace the infinity, we still have to check for the other coins as well, by the way. Okay. So, because we could find something smaller, right? So now we're going to go dp of 2. The current amount is 2, right? And we're going to subtract 1. That gives us, so here we're going to have infinity. We're going to do 1 plus dp, the current amount, minus coins. So that gives us dp of 1. So the dp of 1 is 1. So we do 1 plus 1, that's 2. 2 is smaller than infinity, right? So the dp at 2 is 2. Okay. Remember, we have to check the other coins too. So we're going to do 2 minus 2, that gives us 0, right? So 1 plus the dp of 0 gives us 1. So actually, the minimum number of coins for this position is not 2, but 1. That makes sense though, right? Because we have the amount we need to make is 2, and we have a 2 coin. So obviously, we only need 1 coin, right? And we would check 5 also, but 5 would be negative, right? So kind of irrelevant. Okay, so we'd move to this 3, right? So we'd do, right, 3 minus 1. 3 minus 1 is 2, right? So we'd go 3 minus 1 is 2, so dp of 2 is 1. 1 plus 1 is 2, right? Then we would do, check the other one, which would be the 2, right? 3 minus 2 is 1, so we do dp of 1. 1 plus 1 is 2, and yeah, that gets replaced. And anyways, we keep doing that, right? And so we would get 0, 1, 1, 2, right? 2. I just don't want to make this video too long, so that's why I'm basically skipping over. This is what our array would look like. 2, 2, 3, 3, 2, 3. 3, 3, 2, 3. Okay. And obviously, if you replace infinity with something, you're not checking the minimum between infinity and, like, if you replace, like, if you use a 1 coin and you replace this with, like, I don't know, the dp of the current amount is like 5, then you're not checking, you know, some other coin against infinity. You're checking it against some other coin against 5, obviously, right? Because the infinity would get replaced. So I'm not going to go over this all sequentially because, again, we're checking 3 coins for every position. It'd take me a little bit. And I don't want to waste too much time on this video. But I hope you kind of understand how we're doing this, okay? We're basically we're checking every coin, right? At some position, which is the amount, right? We need to make. We're checking every coin, right? And basically using this formula, right? To basically find the minimum number of coins. And it's really fast, right? It's really fast because we're using previous stored solutions, okay? Which, you know, that's obviously the beauty of dynamic programming. So shouldn't be a surprise that we're using past stored results to, we're using basically subproblems we already solved to solve the current subproblem we're on, right? So yeah. So here's obviously an example where we don't have a valid solution, right? If we have an amount of 3, right? You can't. So we'll go through this, right? This is just like I did up there. Obviously this right here is incorrect. It should be minus coin. So we're gonna start at 1, right? Because we're right here, and so we're gonna do 1 minus 2. right? That gives us a negative number, so we actually never replace this infinity. We do move over to this 2, so we would do 2 minus 2, right? That gives us 0. So dp of 2 is infinity, and we're comparing that to 1 plus the dp of 0, right? So what's smaller, 1 or infinity? 1. So we replace the dp of 2 with 1, which makes sense, right? Because to make up the amount 2, we can just use a 2 coin once, right? Pretty obvious. But that's not what we're solving. We're solving for the amount of 3. So, right, that's why I was saying up here, this final index here that we solve is basically what we care about. But the reason we have to do all this is because we need any of these positions. We need them to calculate the minimum for this position, right? But really, this last index is the very important one. Okay. So when we go to well, this should be 1. So we go to 3, right? We do 3 minus 2. So dp of 3 is infinity, right? And we do 3 minus 2 to be 1. dp of, so 1 plus the dp of 1. Well, 1 plus infinity is just infinity, right? So this remains infinity, right? Well, the minimum number of coins to make up 3 should be infinity, right? And again, this infinity is our placeholder to basically let us know we can't make up that amount, which makes sense, right? If we only have a 2 coin, how can we make up the amount 3, right? And so this is basically a condition we need to check before we return at the end of our program is this last position infinity or not? Okay, so let's implement this. Okay, so again, remember what I said. We're gonna make our DP array, and what is the length of our DP array? It's gonna be amount plus 1, right? Right. And remember, every position in the DP array should initially be set to infinity. So we're gonna say float infinity, right? And remember, the 0th index should be set to 0. That's like our base case, right? Because you need 0 coins to make up the amount 0, right? Okay. So again, we have the current amount. So this is basically us iterating through our array. Okay. And again, we need to check for every coin, right? So we're gonna say for coin and coins, right? We're going to say if the current amount minus the coin is greater than 0 or equal to 0, because again, if it's negative, why we wouldn't ever want to check it. Okay. And here's where we do that formula I was showing you. So we would do current amount, right? That's equal to the minimum between the dp of the current amount and 1 plus the dp of the current amount minus coin, right? And at the end here, again, we want to return the last index if it's not infinity. If it's infinity, then we want to return -1, right? We're going to say dp of amount. And again, the amount is our last position because, right, if amount's 11, then then our array size should be size 12. So dp of 11 should be our last index. So we do return dp amount if dp amount is not equal to float of infinity, else we return -1, because if it's infinity, it means we didn't find a combination of coins that can make up that amount. Okay, boom, that's our code. Pretty neat. Okay, I'm gonna show you this one last time. Okay, so yeah, how we're solving this, right? Feel free to just run through this by yourself or skip back to where I did kind of how we manually did this and how the program works. But the point of me making this video long like this is I just want to show you the flow of how our algorithm is actually working. Like, I feel like other videos don't do that, and actually I think it can be a little bit confusing as to what the hell the code is even doing. But yeah, I hope this helped. It's actually a really neat problem if you understand what each line is doing, right? And what the for loops and everything's doing. This problem shouldn't be hard. Um, right? If it's hard and it feels confusing, you're probably missing something in terms of like not understanding something. So, right, just I would honestly like this is one of those problems. Like honestly, just go through it by hand or like line by line and follow the actual flow of the program. Okay. But anyways, I hope this helped, and I'll see you in the next video. Peace out.